Welcome back, ladies and gentlemen. So hopefully the video on vector addition wasn't too terrible. I know it's a fairly complicated topic, but right now we're going to move on to something much simpler, much more familiar. We're going to be talking about distance, displacement, and time. Compared to the last video, this one is going to be very short, even with me stretching things out a bit by talking about how short it's going to be. So let's take a look. Remember, once again, you have your copy of the notes already. You don't necessarily need to write down everything I'm going to show you. I'm going to write it down in order to be explaining it as I go. So we're going to continue with talking about distance, displacement, and time because these things, distance, displacement, and time, these were key attributes of our initial discussion in grade 10. You guys would have spent a lot of time going over these right at the beginning before you got onto other more complicated topics. We've talked about in the last video how to do vector addition in 1 dimension and in 2 dimensions. Now, of course, we need vectors to add. That's what we need. So we're going to start with distance and displacement. Now, distance is a scalar. Let's use red. Which you remember from our discussion yesterday, review of vectors and scalars, a scalar is something that has no direction. So I could tell you a distance without a direction. I could tell you, 10 meters, but there's no direction component. So distance is broadly the space traveled. That's almost a V. Now, because you end up adding everything, well, let's do a full example here. We'll do it in, let's say green. Green is good. Example. You travel 10 meters to class, 20 meters to your locker, 5 meters to the cafeteria, what is your displacement? Oops, that's the wrong word. What is your distance? Guess which one of the two we're going to use a lot of in this class, displacement or distance? Let's see, which word was the one that I accidentally wrote down instead? What's your distance? Okay, so the formula for distance is going to be d total equals d1 plus d2 plus d3. Hopefully you guys remember this style of writing things, right? So this is subscripts attached to letters in order to explain the various aspects, right? So each of these d1, d2, d3, these correspond to different things that are described in this particular sentence. So d1 would be the first one, d2 the second, and d3 the third. If there were more, we would have more letters. Now, d total is one way to write this, but it's not the only way. We actually could also write it like this. Here, I'll put it off to the side. This is called sigma. It's a letter that is used, it's a Greek letter, and it shows up in mathematics a lot. And it's just a fancy shortcut way to say add everything. I end up usually not even using a capital sigma like you see there. I usually use a lowercase sigma just to make things a little easier because a lowercase sigma just is like that. It looks like a little Christmas tree or a lightning bolt. So lowercase sigma is d1, d2, d3. Basically, this symbol is just a really quick and simple way to tell somebody, hey, everything, add it. Just add it all. Add it, I don't care. And that's it. That's all it means. It just means add. So if that's a little confusing, that's fine. You know, it's been a while. You guys haven't been in class for a while. It's been a while since you did math. Maybe you've never seen that before. I'm going to use it every once in a while. I'll make sure to tell you what it means, of course. I'll remind you. But it's okay if you want to do things differently. This Greek letter, of course, comes in, and it sort of lets us know, like, all right, we can say this here. It says it in the notes, but we'll just quickly do a little sketch here. This means sum of, right? So sum of adding everything together. So we could take our various numbers here and we can put them in. So we've got 10 plus 20 plus 5, so we get a total of 35 equals D total. And that's it. Right, that one's very simple. 35 alone, not enough. We would also need an M, right? Just to say that it's meters. There we go. We're done. That question's pretty straightforward. Again, grade 10 question, review, hopefully very simple. If not, don't worry. Ask questions, right? That's why we're here. But that's distance. Now we're going to talk about the one that I wrote earlier, displacement. Displacement is very similar, but it is more important for our purposes. Displacement is not a scalar. Displacement is a vector with all of the rules and requirements that makes. Everything that we know about vectors, we have to use now. We just have to, use them properly. So that's going to change our definition here. And as it says here in the notes, it says how far you are from a reference. In a straight line. And that part's key. A displacement will always be a straight line. It will always be along a dimension in a direction. So if I pull down the ruler here, right? So here can be my dimension, and a straight line displacement would be from, say, here at this tape to here, my hand. My displacement is from here to there, right? See, I'm comparing them. Remember, as we discussed last time, directions in English are weird. You always do it by comparison. So from here to there is a direction. Now, we could also say break down the direction by using north, south, east, west, and we can try to break it down, or we can use left and right. So for me, this is my left hand. On you guys on the screen, you would see that it's going from here to here, which for you would be right. For me, it is going left. Or we could use north, south, east, west. Now, all of these are, of course, vector components. So all of the stuff we've learned about vector addition applies. For the purposes of displacement, we're going to try something else here. We're still going to use points around the school, not that we're necessarily going to spend tons of time with our locker, since I'm pretty sure you guys aren't getting any this year. So starting from our locker, we go to class. The locker is 15 meters, comma, n. And class isn't spelt right, is -5 meters. So what we see there is two different ways of showcasing the same piece of information, right? We've got it written long style, and we've got it written with a minus sign. Each of those, of course, tells you very similar things, but you have to remember how to use it. The formula that you guys would have learned back in grade 10 talking about displacement was not this one that I'm erasing right now for distance. It was another one that used a Greek symbol. It would have been this symbol. Triangle d arrow equals df di. That triangle has a name. It's another Greek letter. Greek letters come up all the time in math and in science, or physics at least, because it turns out a lot of people who know math also know physics. This means delta, and it means difference. Difference. So difference, of course, has a large and important impact on how we do things. And once again, much like with sigma, remember, sigma meant sum of. It means add everything. So if I give you 10 things, you add all 10 of them. Difference means remove. So this minus that. That's all it's telling us. So in the case of this example here, this whole thing becomes relatively straightforward. We just simply go, okay, my initial position, di, is 15 meters north. Okay, so this is going to be di is 15 meters north. And then I see here, this is my final position when I arrive at class. So that's going to be -5 meters, and that's df. Now, this is always the tricky part that people get wrong when it comes to dealing with the delta, the difference or the change in, is that they put them in the wrong order. It's final minus initial. It's where you end, subtract where you were from. So my final position is -5 minus 15 north. Well, this is negative, but this isn't. Is it positive or negative, though? We have to figure it out. Now, we talked about in the last video how vectors, if they're in the same dimension, which remember is just two opposite directions, we usually say that the positive ones are the ones that are forward or right or up. So the ones that we generally associate with, we'll say, positive things. North is usually on the top of a map. So we usually consider north positive. The negative would usually be south. So this one here could be rewritten as plus 15 meters. Usually I don't like to put the symbols, the units right in the equation, because sometimes it can get confusing. So I'm just going to erase those. So there we go, -5 minus positive 15. Well, negative and a positive, if you guys remember from math class, becomes -15 minus 5. Negative and a negative means this becomes -20 meters. Now, we don't need to put comma a direction because the negative sign tells us the direction. That's the purpose of the negative sign. Its job is to tell us a direction. So there's kind of two ways that you're going to be seeing directions. You're either going to be seeing it as like negative and then the number, or you're going to see the number followed by a comma and then the direction, much as we see right over there. Now, I could rewrite that, so why not? Because this is for review purposes. So instead of 20 meters, or it could be 20 meters, comma, now it's negative, so that will be south. There you go. Either of those would be correct answers. So we have our understanding of displacement, right? Displacement is a straight line. Now, if, again, just for review purposes, and why don't we go into even more detail than normally we would need to, but, it's good to refresh ourselves. It's been a while. If I were to very quickly draw here with my handy ruler a line, there's the line. So it says here that the locker is 15 meters north. Okay, so if I put, let's say, 0 here, and I'm 15. 1, 2, 3, 4, 5. That's about 5, so that'd be about 10. That'd be about 15. Give or take. And it says here that class is at -5, so that would have been down about 5. So 1, 2, 3, 4, 5, about there. So if we mark out what happened, we start here. Oops, start. It's a really good thing I don't teach English, guys. What can I say? And we're going to end there. pretty standard number line stuff. You guys have seen it before. We could also say this is DI with an arrow, and this is DF with an arrow. Reminder, scalars have no arrows on top. Vectors do. That's how we know they're vectors. Right? Those are vectors. So there's the start, there's the end. In order to see what happens, we go from start to end. Pretty straightforward. Looks like I didn't make my dots perfectly straight. Who knew I needed a ruler to draw straight lines, huh? There we go. This line from start to end, this is our delta D. This is our movement from start to end. This is our displacement, and it's a straight line, you'll notice. You'll also notice that it goes 15 down to 0, and then 5 more, which is exactly the number we calculated, -20. So all of this stuff is coming together pretty well. All of this is making pretty solid sense compared to things we hopefully remember in some ways. And the math, I hope, matches with the pictures. Incidentally, there's nothing wrong with drawing out pictures to help you do things. Stuff like this number line is a great idea. You'll also notice that when I was doing this, I tried to make sure to keep the information in one place and then show my steps. Now, there's a few reasons for this. One, of course, this is supposed to be a review for you guys to make sure you guys are ready and you're understanding what's happening. But two, when I come back to this later on, I won't have to try and remind myself what I did because I can see it. So it's not going to be me going, how does this work again? It's me going, oh yeah, there it is. I already wrote it down. It'll help you a lot, especially if you're studying for a test, say. Now, this stuff is review of grade 10. Hopefully this part isn't super complicated, but if it is, it's fine. It's been a while. But for later stuff, when things get really messy, it's probably a pretty good idea to make some time and effort to do that. Okay, so we've only got one more. This one here, we're going to do it real quick. This one is our old friend time. Time is, of course, a scalar. Time is probably one of the most important scalars that you're going to have to deal with because pretty much every question is going to have time in some way or another. Not the same with various vectors and things. Sometimes a particular vector won't show up, but scalars always show up. So, time. How long something happens. Now, this does make me think of something. This is a little point I should add. I'm going to put it in a side box over here. Let's see. I need a couple colors. So when it comes to describing physics with English, there's a few words that are going to come up a lot. This is important. I would write this down. The words are going to be how far, how long, how fast. Each of these statements, phrases, corresponds to a particular variable or term or symbol or idea. How far is displacement? How long is generally time? And how fast is generally velocity? This is, of course, usually confusing for people who English isn't their first language, because how long, well, long can be the length of a ruler, for example, right? I could say this is 1 meter long. But for the purposes of physics, we will usually say this is far. Now, that doesn't sound perfect in English. The grammar's a little off, but we're trying to be consistent to make it a little clearer for people. But if I ask you, how far is that? That means I'm asking you for displacement, or some measure of ground covered. If I ask you how long was that, I'm asking you for time, how long it took for that to happen. Is it a little weird? Yeah, a little bit, but again, English is not always the best language for being clear. So when it comes to time, there are two different types of time that you guys are used to dealing with. Instant and interval. Instant, interval. Instant is one reading of a clock. Interval is 2 readings compared. An interval, let's start with an instant. An instant of time that is very important to all students. 3:32, school ends, done. That is a single reading of the clock, and it tells you something happens at that exact moment. You don't need to know anything else. You just know that as soon as the clock says 3:32, you're done, you can leave. An interval, how many hours is school? How long are you trapped there? Forever. It seems like forever, but it's not. It starts at 8:30, goes to 3:32. We can compare them. Comparing. How do we do that? Well, I would take the final number and I would subtract the initial number. An interval of time is usually delta t, which means it is tf minus ti. Notice there are no bars atop it, right? There's no arrows on the top of each of those. That's because time is not a vector. So time does not have an arrow atop. Now, an instant of time doesn't really need a formula because it's just you read the time on the clock. So like just once. So you don't need to do any math with it. And that's about it. Now, you'll notice, of course, that if I sit here and go, okay, so the final time is 3:32, and let's make it easier. Instead of 3:32, we'll say 3:30. I let you guys out 2 minutes early. Oh, yay. And we'll say this is 8:30. Well, if I do that subtraction right now, we have a problem. Because that's going to be a negative number. And you can't have negative time. Because remember, scalars don't have direction. So how can you have a negative? Negative would mean a direction. That'd mean backwards time. You know, time travel. If you can time travel, let me know in the comments. That might be useful. The reason this works, of course, is because, as anybody will be able to tell you, there's AM and PM, morning and evening. And we're trying to compare across that divide. This would only work if we were to put it in a 24-hour clock, in which case 12, of course, is noon, then 1 becomes 13, 14, 15 is 3. So if I change this from 3:30 to 15:30, now this suddenly gets a lot easier. And, you know, we can take out our trusty calculators because everyone needs to have one for this incredibly complicated math. And we go 15 minus 8, 7 hours, give or take. The 30 minutes, of course, both cancel. So we end up with 7 hours. Technically, it's 6. You're here for 7 most of the time, but 1 hour is lunch, so you guys don't have to worry about that. And that story about checks out, right? Given how many classes you have in a day. So there you go. This is how you would do this kind of mathematics, and you can see a 24-hour clock really does help. Now, in terms of other things you guys are going to do, usually at this point I would have you guys look on page 8 in order to do a little activity. Now, the activity is spent doing a bit of displacement, but in 2 dimensions. You can, of course, attempt this particular activity at home. It's actually doable on your own in the comfort of your own home, although perhaps you're not going to walk quite as far as it tells you to do so. Maybe walk a smaller distance. You can give it a try if you'd like. It's optional. Now, after that, on page 10, we're going to have speed and velocity. And then once we get to that, then we're going to have some questions. But for the most part, at the moment, you guys don't have a lot of practice. So this is going to leave you guys with mostly practicing the vector addition that you've already seen. This information here is just to sort of flesh out, make sure you understand all the basics of what you're already kind of doing math for. So make sure you guys are trying to do some practice there. And I will leave it there for now. A nice and short one. Cheers.